Hi there and welcome from Ventura, California to today's webinar sponsored by KVH Industries, Inside GNSS, and Inside Unmanned Systems, and hosted by WebAttract. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders. Today, we'll be hearing from a recognized expert consultant as he reviews the inertial landscape, explaining contemporary and emerging inertial sensor technologies. Then we'll focus on the high performance at low cost advantages now within reach for applications such as autonomous platforms. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Expert panel session with all three panelists. Now we've invited you along with over 450 professionals from across 30 countries representing a variety of industries, and over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher inside GNSS, Inside Unmanned Systems, would like to take just a moment to welcome you and introduce our sponsor and main moderator for today. So over to you, Richard.
Thanks so much, Lori. Appreciate that. On behalf of Inside GNSS, Inside Unmanned Systems, and today's sponsor, KVH, I extend a warm welcome to our audience from around the world for today's web seminar. We really value your participation. We're delighted you're with us today. Now, I'd like to introduce Sean McCormick. Mr. McCormick is the Senior Director of Global Inertial Systems, the Inertial Navigation segment at KVH Industries. Hello, Sean. Welcome.
Good morning, Richard. Good morning, everybody. I'd first like to welcome all the participants and panelists on behalf of KVH Industries. Very glad to have you here today. KVH is a leading innovator for high-performance sensors and integrated inertial systems, delivering extremely accurate position and assured navigation for various autonomous platforms. Having produced more than 120,000 fiber optic gyros for standalone systems and fully integrated inertial solutions, KVH fogs and fog-based IMUs are in use today in a wide variety of applications ranging from optical, antenna, and sensor stabilization systems to mobile mapping solutions and autonomous platforms spanning across land, sea, and air. Continually investing in our products is key, preparing for future market needs and ensuring only the highest level of reliability through extensive testing and qualification. KVH will be releasing our photonic chip-based technology into our higher performing inertial measurement offering in Q3 of this year. We'll share a bit of this with you today and hope you find this webinar beneficial to your own development efforts. Thank you again for your participation. At this time, I'll pass it on to our moderator to begin.
Thanks, Sean. Appreciate those comments. That's exciting news. I'd like to introduce today's moderator extraordinaire, Alan Cameron, who happens to be the editor-in-chief of Inside GNSS Magazine and the PNT editor for Inside Unmanned Systems. He's covered GNSS, PNT, sensor integration, autonomous industries, autonomous applications as a writer and an editor since 2000. Alan, welcome. The floor is yours.
Thank you, Richard, and thank you, Sean. Welcome to everyone around the world. I see we have international participation. That's always very heartening. We're here to talk about micro electromechanical inertial measurement units, MEMS IMUs. MEMS IMUs represent the single biggest guidance, navigation, and control advance over the last 20 years. That's a big assertion, but we're going to back it up. It's opened up a lot of new applications to inertial technology, and as you'll find out, if you don't already know, during the course of this broadcast, it's opening up even more with recent developments in photonic technology, making inertial technology available in even more applications, particularly those where swap, size, weight, and power requirements are rigorous. But photonic technology is getting inertial in there, and it's quite exciting to see these developments. Before we get underway with our webinar, let's find out a little bit about our audience. Lori.
Absolutely. Coming up on your screen is the first of our polls for today. If you wouldn't mind weighing in on the following question: which operational environment provides the greatest need for inertial solutions? Is it UAS drone aviation, autonomous ground vehicles, marine and subsea, or industrial robots? So coming in with 43% UAS drone aviation, 34% autonomous ground vehicles, 15% marine and subsea, and 9% industrial robots. Alan, any thoughts here?
Well, this question is what our British friends might call a poser. It's a pretty difficult question to answer because all of the candidates, I would say, with the exception of the last one, industrial robots, all of these environments represent a great need for inertial solutions. And I would say we had a bit of a hidden agenda with this question because I think people answered according to which environment they are most active in. But we'll leave that up to debate. Certainly, drones need inertial. Autonomous ground vehicles do too, and marine and subsea, it's pretty hard to live without it. So I think what this answer reveals is the participation of various segments of our audience in these particular sectors. Well, we'll find out more as we go through the webinar. We're going to hear today from three speakers: Ralph Hopkins, Skip Ashton, and Roger Ward. First up is Ralph Hopkins, a distinguished member of the technical staff and a group leader in the Positioning, Navigation, and Timing Division at Draper. Ralph is responsible for the design and development of inertial instruments and sensors. He has served as Technical Director of Advanced Inertial Instrument Development Programs, including strategic, navigation, and tactical grade gyroscopes and accelerometers. He is an invited speaker for short course tutorials on inertial instruments and inertial technology and has presented internationally for the NATO Science Technology Organization sponsored lecture series and symposia on navigation technology. He holds a bachelor's and master's in mechanical engineering from Rensselaer Polytechnic Institute, a master's in engineering mechanics from Columbia University, and a master's in engineering management from the Gordon Institute of Tufts University. Ralph, please proceed with contemporary and emerging inertial sensor technologies.
Thank you, Alan. Good morning, everybody. Our discussion today will start with an overview of the current inertial sensor landscape, namely what types of gyros and accelerometers are employed in different applications and performance grades. Then we'll get into small form factor inertial sensors, specifically MEMS devices. We'll touch on a couple of emerging technology trends, specifically those that are being explored which may have potential in improving the performance of miniature gyroscopes and possibly enabling the miniaturization of optical gyros. And we'll close with some thoughts on inertial navigation augmentation and where sensor development is headed from here. This chart is an attempt to capture the performance and application space of different gyroscope technologies. We have the two key inertial sensor performance parameters plotted on the two axes. We have bias stability here on the x-axis, scale factor stability here on the y-axis. So in the region of the origin, we're in an area of very high strategic grade performance. As we move out diagonally, we enter into the navigation grade and coarser tactical and consumer grade performance regions. And this chart illustrates what I like to call the small gyro problem, in that miniature MEMS technology hits a performance wall at roughly around 1 degree an hour bias stability range. Higher performing gyros are all larger scale devices, such as optical and good old-fashioned spinning wheel gyros. And this is in contrast to the corresponding situation with accelerometers. Here we have the same plot with bias stability on the x-axis, scale factor stability on the y-axis. And notice that the miniature MEMS technology penetrates quite deeply into the higher performance application space and really covers a very wide performance regime. This chart here, we have some examples of some of the miniature MEMS gyroscopes that have been developed over the past 20 years or so. All of these are Coriolis vibratory gyroscopes in that they employ a vibrating transducer element such as a ring or a tuning fork that's driven at resonance. An applied angular rotation rate introduces a Coriolis force loading on the resonating element, which by structural design couples into an orthogonal resonant mode whose response is an indication of the applied rate. Likewise, some examples of MEMS accelerometers are shown here. Some of these use tension and compression in vibrating beam elements to indicate acceleration via shifts in resonant frequency. Others simply use the measured deflection of a flexure-supported mass to indicate acceleration. So if you're in the business of making miniature MEMS gyros and accelerometers, well, you're going to make a MEMS-based IMU. And this has been the single biggest development in position, navigation, and timing in the last 20 years, namely the ability to add a guidance, navigation, and control function to vehicles such as artillery shells, UAVs, and so forth, where it was previously impractical to do so because of size, weight, and power considerations. The United Technologies and Honeywell IMU shown here are examples of gun-hard products capable of surviving firing launches up to 20,000 Gs. Some of these other IMUs are integrated with GPS receivers, which then furnish a GPS inertial integrated solution that has GPS limited position accuracy. This next chart shows some initiatives in miniature gyro development that are intended to squeeze better performance out of a miniature transducer element. These are all Coriolis vibratory gyros of the ring resonator type that are somewhat inspired by the hemispherical resonator gyro, a very high performance bulk size gyro that uses a wine glass shaped resonator. If you take one of your nice crystal wine glasses at home and flick the rim with your finger, you'll hear a nice clear tone ring out. But actually there are two vibration modes going on that lie spatially at 45 degrees to each other. And if you listen carefully, you may hear a lower frequency wobble, which is the beat frequency between those two modes. If you rotate your wine glass along the axis of its stem, you'll introduce Coriolis loading on the rim, which drives energy from one of the wine glass modes into the other, causing a precession of the net mode shape around the rim perimeter that's measured as an indication of the applied rate. The top two designs shown here are silicon MEMS versions of that idea collapsed down to a 2D planar structure that you can think of as a vibrating onion slice. Improved performance is achieved through more transducer mass per unit volume engaged with sensing the applied rate. These lower two gyros are attempts at miniaturizing the wine glass directly and incorporate novel new microfabrication processes, namely CVD thin film diamond processing, and over here, a micro-scale glass blowing process. The ability to control the resonator uniformity and or trim or tune the resonator frequencies will be the key to victory in these designs. Optical gyroscopes are a big part of our webinar discussion today, and normally they are not thought of as candidates for miniaturization because they derive their performance through their size. The total optical path length and the diameter of the optical path length control overall sensitivity. However, there is an optical gyro architecture that's a hybrid of the conventional ring laser gyro and the interferometric fiber optic gyro that has potential for miniaturization while maintaining higher performance. The ring laser gyro resolution is controlled by the sharpness of the optical cavity, or finesse. Ring laser gyro optical path length is short, but high resolution is achieved through multiple passes of the light in the resonator cavity. IFOG resolution is driven by the overall path length. The interferometer output is formed with a single pass of light. but high sensitivity is achieved through long path length. So employing a fiber coil as a ring resonator then versus an interferometer combines the best attributes of both architectures. You have multiple passes of the light forming an optical resonator of very long path length. The combination of these two features would permit a smaller diameter coil without sacrificing sensitivity. There are two challenges associated with this RFOG concept. The first is optical fibers that allow for tighter bend radii, but there are such fibers in development. Some of these are smaller diameter fibers with proprietary design features that maintain the needed optical index of refraction difference between core and cladding under the high stress conditions associated with a tighter bend radius. There are also photonic crystal and air core fibers under development that sustain very tight confinement of the optical wave under sharp bend radius conditions. The second challenge to miniaturization is shown on the next slide, namely the need to miniaturize the associated discrete optical components found in fiber optic gyros. For example, the laser sources, photodetectors, optical couplers, phase modulators, and so forth. You're starting to see FOG vendors employing photonic integrated circuits to miniaturize the off-coil components, such as in the KVH example shown here. And we'll be hearing a lot more about this from our next speaker. Also, the emergence of the hybrid silicon photonics technology that enables fabrication of photonic components directly on low-loss waveguides has promise for form factor improvement. The SOI substrate is like a printed wiring board, and the CMOS layer is like the active circuit components. The photonics chip is laid out such that the CMOS devices are positioned over regions where the substrate waveguides neck down. This pushes the optical field up into the active device where the electric field can be detected or amplified or manipulated to modulate the optical phase front. So the miniaturized front ends enabled by photonic integrated circuits and tighter coil diameters enabled by new fiber optic technology, it's conceivable you could see FOGs in a bottle cap size form factor. Aside from miniaturization, the photonic integrated circuit technology offers significantly improved reliability and reduced production costs. So we have these terrific new miniature IMU products available to us that are driving new application areas: personal nav systems, search and rescue robots, autonomous vehicles. And with these miniature IMUs, we have a handle on the size, weight, and power requirements of the mission. But look at the position accuracy required, very high position accuracy on the order of 1 meter to 10 meters. And oh, by the way, GPS availability, either intermittent or denied altogether. These mission goals flow directly from the application space. If you're underground or in a building, GPS won't be available. Yet you need very good position accuracy because you want to know if you're on the 5th floor or the 6th floor, or am I on this side of the wall versus that side of the wall. So when GPS is denied, an inertial only solution isn't going to cut it. So augmentation is required, as discussed in this next chart. Here we have some examples of position error growth shown as a function of 3 different system cases. And this first case up in the upper left-hand corner shows an inertial only solution using state-of-the-art gyros and accelerometers. Bias stability on the order of 0.001 degree an hour, and accelerometer bias stability on the order of 1 micro-G. And this shows that just after 1 hour's time, the position uncertainty for an inertial only solution grows to approximately 60 meters. Not acceptable for a personal navigator solution. Also, that type of inertial sensor performance is not currently available in a miniature form factor. The second plot over here on the upper right shows a position solution with tactical grade inertial sensors of the performance category available in a miniature system. with intermittent GPS updates applied every 2 minutes. And this shows a peak error of about 40 meters, still not good enough. The third case down below shows tactical grade sensors with the addition of a velocity meter to the navigation solution, a velocity meter such as a LiDAR, for example. And now we have position error of only about 10 meters after an hour's time, which is approaching mission goals. So this illustrates the likely solution to these personal nav systems will be a suite of sensors such as a velocity meter, a magnetometer, an altimeter, all integrated with the GPS and inertial in an optimal nav algorithm to furnish the most robust solution to span GPS outages. To conclude, the MEMS inertial has proven to be a disruptive technology that has led to a whole new application area in the guidance, navigation, and control industry. It has enabled the insertion of a GNSS function on vehicles where it was previously impractical due to size, weight, and power considerations. We briefly touched on some tech trends associated with the relentless and enduring imperative of pushing performance improvements in inertial components, specifically gyros. Many of the emerging application areas for integrated navigation systems feature a GPS-denied scenario that will drive hardware solution architectures that incorporate a suite of augmentation sensors where the inertial instruments serve as just another chipset in the overall design. The value prospect for developers then is in the overall integrated system performance, not the individual components. Thanks for listening, everybody. It's been my pleasure. Over to you, Alan.
Thank you, Ralph, and thanks especially for that gyroscope emerging tech application slide. I've seen that a few times now, but I never get tired of looking at it. We have some questions come in for you already. We'll turn to those shortly. Right now, we're going to hear from Skip Ashton, VP of Product Development at KVH Industries. Skip is responsible for engineering development programs and delivery of products to market. He was previously Vice President of Software at Silicon Labs, responsible for the company's software and quality assurance teams for both MCU and wireless software and tools. He was the technical lead at Zigbee and Thread and was deeply involved in the developments of Zigbee Pro and the Thread stacks, as well as the application layers that were developed for those commonly used IoT devices. He studied at Georgia Tech and spent 5 years in the U.S. Navy nuclear program. Skip, take it away.
Thank you, Alan, and great to be here today to discuss the PIC and the testing that's gone on through this. So I'm going to cover what is the PIC, the Photonic Integrated Chip, just briefly, our criteria for the PIC testing and how we settled on that, the testing itself and how that integrated with manufacturing, ramp and tooling, and the lessons learned from that testing. So the PIC itself, we've seen some of these pictures before, you may have, is really about taking a number of hand-built products, the linear polarizer, the couplers, and some of the splices in there, and really using the scale and mass volume potential of semiconductor processing. So we can replace those hand-built parts with this integrated device. We can simplify the assembly and testing process. But instead of normal semiconductor assembly and package processing, we've got optical surfaces. So the pictures on the right-hand side there, the PIC is on the right and the fiber array is on the left. And the fiber array is commonly used today in telecom, and there's various companies that make these, and you can customize the design, and you can see in the upper picture the fiber coming through the fiber array, and that's aligned into the PIC on the right-hand side there, and you see the diagonal lines there are actually stray light suppressors from that interface. And the bottom picture shows the edge view of that with the fiber array lid on the top, holding those fibers down and then mating up to the PIC with that. So PIC testing is an interesting problem. Semiconductor testing is very well defined, and JEDEC is used around the world by lots of companies, and it tests the device, it tests the package, electrical characteristics of the device, strength, and lifetime. And you really can't sell a semiconductor product today without evidence of these tests. But many of them really don't apply to an optical part, or the conditions are kind of stringent. So to accelerate life testing on a semiconductor, you may run it up to 130, 140 degrees to accelerate the life testing, and that's a little more difficult to do with some of the optical components and fibers and things. On the other hand, we've got optical testing defined in Telcordia standards, and that's also a pretty well-defined set of tests. And the PIC is really a combination of both these semiconductor and these optical tests, and has to reflect the design and your expected failure mechanisms. So the testing, really should reflect what you expect out of your product standards and the requirements. And so what we call our DVT testing, the design, validation, and test, is to validate the design, but also the process limits and acceptance to be used. So for KVH, right, this was a critical step. So there was obviously quite a bit of testing conducted, and I'll give you a bit of summary of that. In addition to early engineering testing, we took parts and put them in risk reduction testing, which was early design units that we put into temperature cycling to allow evaluation while the design and manufacturing flow were being finalized and updated, and we went through some different variations of the design. And then for the DVT testing, we defined for the PIC and fiber array set of tests, temperature cycling from minus 55 to 95 for 1,000 hours, temperature and humidity, where we went at 55 degrees Celsius and 95% relative humidity for 264 hours. We're doing shock on all axes, different levels of shock from the mill standard. We're doing vibration, 2 hours on each axis. And then, of course, we've got to do gyro build and characterization of those. And we also added shear testing of the PIC and fiber array joint, and I'll discuss a little bit how we ended up with that. So DVT testing is really intended to be done on the finalized design, and it's both at the part level and at the product level, and using the final manufacturing flow. But there's a bit of a feedback loop here, because we need a lot of parts to do DVT testing, and for that, right, we need to then optimize our manufacturing flow. And so it takes time and some iterations to get through that process. And then our DVT testing also included other parts of the optical assembly just for completeness and to ensure we were hitting everything in the design. And part of this is testing of sufficient quantity of materials to provide confidence in the results in the manufacturing process. And this really is taken right from some of the semiconductor processes, where you typically use 3 lots of semiconductor wafers built at different times so that you can analyze the variability in wafer to wafer and lot to lot from a given manufacturer. And we took that one step further because we actually did 2 PIC designs with different suppliers and process technologies. So many of the semiconductor processes you're used to for standard chip production today at large fab houses like TSMC, you would never think of doing 2 because those processes are very mature and marching down Moore's Law and things. This is something where there's different design rules at different process houses, and your design has to reflect those. And so completing 2 PIC designs not only gave us 2 different suppliers and design rules, but also gave us diversity of supply chain. So step 1 in our whole process here is really incoming parts validation. So we've got to test our parts before we put them into assembly to ensure they meet our design intent and the optical budget for the overall system. So for the PIC, that means we can evaluate it using wafer test structures. We can put test structures on the PIC themselves, and then we can do free launch into individual parts and measure them discretely. For the fiber array, we can take those in from the supplier and measure them individually for acceptance. And for each of the parts, we track the supplier test results, our own incoming inspection results, and each step of the manufacturing process, there's manufacturing validation measurements, and then there's final tests of the individual assembly as they're put together. And these are all put in a database so we can track them throughout. And the key parameters, of course, are related to the optical budget. So we're looking at power loss, insertion loss, extinction ratio, the split ratios of the couplers, and repeatability of these things over temperature. Okay, and let me turn this back over to Alan for our first break.
Thanks, Skip. We will resume with PIC reliability and testing in a few minutes. We're going to have a few questions now from the audience, and I'd like to encourage everyone in the audience, if you have questions, please input them, type them in, and we'll get to as many as we can during the course of the broadcast. Harkening back to you, Ralph, in your presentation, why is it difficult to achieve high performance in a miniature gyroscope?
Yeah, so we mentioned with the optical gyros that the overall sensitivity is really controlled by their size, the total optical path length, and then the diameter of the optical path length, both combine to control the sensitivity of optical gyro. In the case of a mechanical gyro, the mechanical transducer element, the sensitivity of it scales as mass times length squared versus an accelerometer, which sensitivity scales as mass times length. So as you shrink a mechanical transducer element that you're employing as a gyroscope sensor, you start chipping away at its sensitivity at a faster rate than you do with accelerometers in the accelerometer case. So that's why miniature gyroscopes are a tougher ask than miniature accelerometers.
And in that regard, can you go a little further into the challenges of developing a resonating optical fiber gyro?
So in a conventional interferometric fiber optic gyro, the optical source lies outside the pathway of the coil, and you launch the light into it. And a gremlin in fiber optic gyros is backscatter. In the interferometric fiber optic gyro, the light source is intentionally broadened. The wavelength distribution is intentionally broadened to desensitize you to backscatter errors. So you have a very short coherent length source. So the only interferometer that's formed is within the coil. In the resonating case, you need a very narrow line width laser to develop the optical resonance in the coil. So you're then vulnerable to backscatter sources from splices and components forming local interferometers that are going to serve as an error source. So what you see some RFOG developers doing is developing different types of modulation schemes so that the clockwise and counterclockwise wavefronts, when they're processed, reject the sideband beat notes that form from backscatter. So the backscatter effects occur at frequencies that are much greater than the rotation response. So there's some fancy optical processing that needs to be employed in the resonating fiber optic gyroscope case.
All right. We're going to hear a little bit into the future. We're going to hear about the future of fiber optic gyros, but first a little bit more about PIC reliability and testing, and a question for you, Skip. How do you define if a product is reliable through this DVT testing?
Well, thanks for that. And so, we really took a cue from the semiconductor industry where you have really a two-step process here where reliability has to be defined first with each part in the system. And that's why the DVT testing included each of the parts in the optical assembly and putting them through their stress and design validation testing. And only when they pass that do we then put them into the full-up system. And of course, the system reliability is more a sum of the parts, including the electronics and mechanical parts and things like that. And so you have to build from the bottom up, but only by making each part reliable can we then get to a top-level analysis to improve the reliability of the overall gyro.
And further, Skip, what are the next steps in PIC development and integration?
So Roger will hit some of this in his, but this is really the first step in integration of the PIC, and it's a longer-term project to, as Ralph has talked about, continue to miniaturize as many of the components possible. So we look at this is the beginning, and you'll see from our testing results, we view this as a very long-term process of continuing to integrate more and more parts of the gyro to miniaturize it and improve performance.
All right. We'll be back to you, Skip, in a moment, or in a few moments, with more on PIC reliability and testing. And after that, we're going to peer into the future of fiber optic gyros. But first, Lori, let's have another input from the audience.
Yes, let's do that. So folks, coming up on your screen is that second poll question. In this case, there is a select all that apply, but we're asking on your honor system to select your top two. So what are the two most important qualities of an inertial sensor for autonomous vehicles? So go ahead and give us your top two choices: low bias instability, low angle random walk, low noise, high scale factor. So I got a front runner there with 78% low bias instability, followed by 59% low angle random walk, 33% low noise, and 12% high scale factor. So any thoughts here, Alan?
Well, I think what the underlying aspect that this question reveals is that most of our audience is involved in the application realm. Obviously, low bias instability and low angle random walk are the key factors or key parameters you want to look at in application of inertial technology. So that's where most of our audience is at. But I think we have some people in the manufacturing or integration realm because at least a little bit more than 10% are listing high scale factor. That's a manufacturing concern. Of course, low noise is going to be present in almost any concern, but yeah, this I think we're looking at an audience that is primarily involved in applications, and there's going to be a lot of interesting material for them in the third part of our presentation when we look at the future of fogs. Right now, let's go back to Skip and the conclusion of your presentation, Skip, on PIC reliability and testing and the release to manufacturing, where the pedal hits the metal, so to speak.
Great, thank you, Alan. So I wanted to give you a better understanding of our test process and validation. So here's one of our test matrices, and we have two parts configurations for testing. And for each of those part configurations, we built two sets of 20 parts. And going into that, of course, we have to measure and validate each of those parts. One set of those 20 parts went into temperature testing. Another set goes into the temperature and humidity testing. When they come out of that testing, they again get measured and validated. And then we took the set from temperature and humidity and we used it for shock. We measure and validate it again. We use it for vibration, and we do a final measurement and validation. And what we're really looking, of course, is what changed pre-test to post-test across all of those. And so this step-by-step testing and validation was done across these different parts and across different configurations in kind of a methodical method here, and with larger sets of parts, as you see here, the sets of 20 parts, so that we don't really like testing one or two and then trying to understand the results from that. It's much easier when you have a larger set. So what kind of measurements do we need to take here? Here's some of our typical measurements. On the left-hand side, we've got extinction ratio over temperature over 2 cycles there. And on the right-hand side, you've got power over temperature. And so we actively measure the extinction ratio and the power out of the fiber ports over multiple temperature cycles from -45 to 80 degrees Celsius. So this is an overnight test with the we're running the parts in the chamber, and we're actively monitoring them outside the chamber. And so this takes a bit of time, as you might expect. We can run multiple sets at a time, of course. And then you get into the overall results. And so the chart on the left here is showing different wafer IDs from one manufacturer. And we've got the average loss from the PICs we've worked on for each of those wafers, the minimum ER we saw for the assembly, the insertion loss repeatability over temperature. So that's a measure of how it changes over temperature. And then in the final column there, you see the power balance, which is a reflection of the coupler. And then the chart on the right is the loopback loss, and you see kind of a nice distribution settled around 16 dB there, and that's us measuring the overall loopback loss, the overall assembly, to get an idea of the how the optical budget is doing. But you see some nice normal results there in that kind of distribution. So I mentioned at the start of this, of course, the manufacturing process development. So DVT obviously is needed to validate the design, but really here, remember, the point is we want to be able to produce this reliably in volume. And that requires a real joint effort between engineering and the manufacturing. And so this whole process started with manual assembly and validation of the PIC and the PIC design and fiber arrays on the benchtop, right? But we can't expect to build in mass production that way. And so we purchased an automated alignment machine that you see some pictures of there. And so this process the machine does a visual inspection of both the PIC and the fiber array. We launch light into one of the fibers of the fiber array and do active alignment coming out of that entire assembly between the PIC and the fiber array while it does active alignment of that joint. And when it has it properly aligned and gapped, it applies the adhesive and cures the joint. And so that entire process of how best to align it, launching the light in, the adhesives to use, and the curing process are a good example of a joint process required between engineering and manufacturing as part of the DVT effort to make sure we can build these consistently. So what did we learn from the DVT testing? So as I mentioned, we did a lot of engineering testing and design validation to reduce the risk with DVT, but it didn't uncover all the issues we found. In particular, humidity testing revealed a weakness in the PIC fiber array joint that was not seen in other testing or validation, wasn't even seen in the gyros we built in the early days with alpha units that went through vibration and things like that. But that's the point of doing this kind of extensive part-by-part testing. And so once we found that, that required us to double back on the process a bit, change the adhesives in the assembly process to increase the robustness of the joint. And I mentioned we added shear testing. And so that shear testing of the PIC fiber array joint was a way for us to get a better, quicker measurement of the strength of that joint and the adhesives and the assembly process without waiting for a 264-hour humidity test. Because the problem with 264-hour tests is they really take 264 hours, and there isn't a great way to speed them up. So we added shear testing as part of the DVT to give us a quicker indication of that. The other important lesson from all of this is building larger batches of parts provided us much better visibility into the manufacturing yields, the process improvements. So it's important for DVT that you do larger batches of parts, but it's also a critical development step between the teams so that we get the right process on a day-to-day basis out there. And so that effort really required close cooperation between the optical teams, the mechanical team, reliability engineers, and the manufacturing engineers to make sure we could build this properly. Of course, I've been talking a lot about individual parts testing and how that builds up to reliability, but that's only part of the testing. Right? Once we've completed that individual parts testing and really in parallel with that, the final proof is in operational gyros. Nobody's buying individual parts for us. They want to buy an operating product. And so we want to build and have built numerous gyros with different configurations of the parts and of sufficient quantity to allow us comparison both between these different parts configurations and with our existing manufacturing data. And of course, now we're moving on from those optical measurements we're doing on the part level and relating those to what we expect at the gyro level, bias, scale factor over temperature, the linearity. And this longer-term reliability at the gyro level, of course, is built up from this parts reliability that we learn about through the DVT and that overall assembly of the optics, the mechanical, the electronics, and the software. So we continue to do that. So our current status on this DVT is we've completed our initial DVT efforts. And as Sean mentioned at the beginning, we're releasing the PIC into products. So we're generally done with that, finalizing our results and finishing up all that paperwork, the part everybody loves there. We will continue to do ongoing testing to monitor the design through early manufacturing. And really the point of that is to improve the yields and the process controls, any further improvements on performance, and we can adjust our acceptance criteria as we continue to increase the sample size and lot sizes. And so this is an ongoing joint effort with both engineering and manufacturing as we continue to monitor that. So thank you for that, and let me turn it back over to Alan.
Thanks very much, Skip. And with the release, as you mentioned, of the photonic integrated chip into actually available products, we're opening up a whole new realm of applications for fiber optic gyros. And here to tell us more about that, Roger Ward, Director of FOG Product Development at KVH. Roger has broad experience leading global development teams, programs, and portfolios and service solutions. He's known for building high-performing teams to drive efficiency and results in commercial, defense, and international markets. He has directed product portfolio pipelines, funnel, roadmaps, and strategy for new product launches, including KVH's Photonic integrated chip effort, resulting in the groundbreaking PIC-based fiber optic gyro. Roger has an MBA from the University of Rhode Island and a bachelor's degree in mechanical engineering from Clarkson University. Roger, take us into the future.
Thank you. So today I'll be talking about the future of KVH fiber optic gyros in respect to the emerging autonomous navigation markets and applications, and discuss how the new photonic integrated circuits enable a more scalable, affordable inertial sensing solutions. So we heard previously a lot about SWAP, which is a key consideration for product development, but there are other things to factor in, such as manufacturing, scale, and price. So we'll talk a little about that. So KVH is a leader in the manufacture of open-loop fogs and has been a pioneer in affordable, high-performance commercial fogs. KVH is best known for its compact, rugged, exportable, tactical-grade fogs. A little bit of our traditional product line is shown here, which includes single and multi-axis fiber optic gyros, inertial measurement units, and inertial navigation systems for commercial and military dual-use applications. So KVH understands inertial sensing needs for continuous navigation and guidance. For example, our TACNAV products are used in armored vehicles to provide hours of uninterrupted precise positioning, heading, and orientation during GNSS disruptions. Okay, talking about dead reckoning for a moment, precision inertial sensing using fogs allows you to meet both mid and long-term dead reckoning needs for continuous autonomous navigations. By that I mean hours and minutes of outages of GNSS. This is key for vehicle or drone safe operation, such as in urban canyons during loss of GNSS, particularly in all weather, such as snow or rain or other conditions that can degrade optical sensors and radars, LiDAR, for example. KVH fogs meet the autonomous market needs for performance. But the challenges are, how do we achieve a better price? How do we achieve manufacturing scale for the new and emerging markets? Silicon photonics allows us to rethink fog performance, manufacturing scale, and price. The inherent ability to design and scale fog performance up and down using different components such as coils, SLDs, and other devices, allows for new flexibility in product performance and pricing levels. So I'll discuss this in a little bit more detail. As Skip talked about, the photonic integrated circuit replaces the all-fiber couplers and polarizers with a very small silicon photonic waveguide. What's key about KVH's silicon photonic waveguide is it's very low loss. It has high performance characteristics that allow us to scale fog performance using different types of fibers, different lengths of coils, and lower price components. The telecom industry has proven silicon photonics and the microfabrication and process controls to achieve very high volumes and economies of scale. What's different with KVH is we're not operating at the telecom wavelengths of 1050. We operate at shorter wavelengths, which allows us to reduce the amount of coil length to achieve the same levels of performance. So PIC enables KVH flexibility in fog product manufacturing and cost points. As Skip pointed out, flexibility in supply chain with both U.S. and international suppliers has recently been shown quite important as a result of the COVID-19 impacts. PIC fogs continue. Manufacturing development at KVH continues on PIC fogs as we work towards higher levels of automated manufacture. So skip some of the semi-automated manufacturing that are employed today. And Richard was talking about future developments of hybrid PICs, which we are working on, which will allow us to scale manufacturing volumes to those anticipated in the future. Looking at transportation trends and where the market is going, the emerging autonomy market segments have different needs. So talking about mobility as a service for a minute, it's a major shift from personal cars to ride sharing, shared public and private transport services. So today these primarily operate in urban areas with ride sharing, for example, Uber, Lyft, Mobileye, those kinds of things. From a size and from a price standpoint, the objective is to be the service to be less costly than taxis, but because it's ride sharing, your cost can be higher than an autonomous vehicle. In autonomous vehicles, there's a major shift to self-driving vehicles with much lower cost per miles. For example, long-distance trucking is at the forefront of this adoption. Autonomous vehicles are combining a variety of sensors today, and standardization is expected as they move towards mass production. So the transportation trend in service, vehicles, and aircraft for autonomous navigation is really a paradigm change. It's reinventing traditional products and partners, which presents new opportunities and challenges. The rollout of these technologies are not just technical. Regulatory, legal, and other challenges persist. Looking a little closer at autonomous vehicles, as you all likely know, it's a very disruptive technical innovations, major investments, and major potentials for autonomous sensors to support driving, and a transformative change in autonomous vehicle navigations. So KVH sensors have been involved since the early days and have been used to drive millions of autonomous miles. Our inertial sensing provides continuous all-weather open road navigation solutions. As we look forward to this market, we hope for potential benefits face challenges that may slow the widespread early adoption as originally predicted. There are technical challenges on how to best understand and act on multiple sensors and information sources while lowering the marginal costs. There are societal challenges such as the regulatory and government uncertainty. And there are seriously business challenges as we anticipate a shakeout of many of the new entrants on certain markets and technologies. Looking at shuttles for a minute, their fiber optic gyro product needs are a bit different than autonomous cars. Today, they generally operate in large cities, which are geofenced rather than open road conditions. Fog size and fog cost are not as challenging as autonomous vehicles, cars, are expected to be. Today, KVH is already used in many successful mobility shuttles and minibuses. Looking at the autonomous aircraft market, which was a major interest in our early poll. So autonomous aircraft today are used to perform dangerous or difficult work to do, such as military drones and UAVs that operate with different degrees of automation. Civilian autonomous aircraft and drones, however, far exceed those of the military. Their uses are rapidly expanding for commercial, scientific, recreational, agriculture, and other applications like surveillance and product deliveries, aerial photography, infrastructure inspections. Again, the fog product requirements are a bit different than autonomous cars or buses. Usually, small size, low power, and lighter weight are very key, particularly for smaller drones. The development of the autonomous aircraft is presenting new opportunities for partnerships that combine traditional aircraft manufacturers or airframe suppliers with autonomous navigation innovators like KVH. Okay, as we look at how to package our photonic integrated circuits into our product line, KVH is looking at the various market segments that offer different opportunities. As you can see here, robotics and agriculture are relatively large markets with moderate growth rates, which could be very attractive. Construction is a very fast-growing but still small opportunity. Pipelines are small and steady. So this is the kind of information that factors into the future fog products that KVH is looking to launch. Talking a little bit more about performance for autonomy in our fog products. The scalable PIC fog performance that's allowed means we can tailor the performance for different needs. So focusing primarily on continuous autonomous navigation, which is when inertial sensors can shine. Inertial sensing offers very fast update rates, 1,000 times or more a second may be needed. It offers precise positioning in all weather conditions. If you look at some of the technical performance, for example, parameters, ARW is shown in the chart on the right. It shows you why you need very low noise fog in order to meet the precise positioning needs. So 4 centimeters is what's typically called for today or expected to be needed for safe navigation. 4 centimeters is a very challenging performance to meet in all conditions without GNSS potentially. So as we look at KVH's role in autonomous navigation, KVH is looking to reinvent to meet the evolving autonomy markets and needs. KVH is already part of the autonomous world today, and we're working with many autonomous navigation companies. KVH is looking at the renaissance of fogs using photonic integrated circuits to make a more scalable, more affordable inertial fog. Today we are focused on flexibility and performance, ranges, reliability, and manufacturing scalability in the new products that we plan to launch. So with the development of a robust, high-performance silicon photonic-based fiber optic sensor, KVH believes there's no limit to how autonomy will continue to impact and improve lives. It'll allow us to continue to do dangerous jobs. So you can stay safe. To bring freedom of movement to those who can't or choose not to drive. And it's leading the way to an exciting future. Thank you. To you, Alan.
All right. Thanks very much, Roger, for that look into the future. For the benefit of our audience now, we have a number of resources available to delve further into photonic chip technology. A nice ebook that KVH has put together looking at the threats of GPS and GNSS disruption, which is the issue of the moment for many inside GNSS readers. An application story about the RoboSub, and one about shuttles. We'll leave that up there. Of course, I want to add that these slides will be available to you, so if you're not quick enough with your pen and pencil, you'll get these links in very shortly when the webinar slides are delivered directly to your inbox. I want to encourage all the audience to submit more questions for the panelists. We have some questions coming up soon. But first, some more questions for the audience. Lori?
Absolutely. Coming up on your screen is our third and final poll question for today. And that question is, of three primary mobility as a service domains, which will mature the fastest? Autonomous cars, autonomous shuttles, or autonomous aircraft? All right, it looks like our front runner there is 56% autonomous shuttles, followed by autonomous cars and then autonomous aircraft. Any thoughts here, Ellen?
Well, this is in line with what I would expect because autonomous shuttles are coming online very quickly. There are a number of them operating out in the world, and people can jump on board them and take a little driverless ride to get a taste of what's coming. So autonomous shuttles are with us currently, and if you haven't seen one in your neighborhood yet, keep your eyes open. They are spreading pretty rapidly. Autonomous cars, going to take a little bit longer. There are a lot of pioneer developments in the works and a few actually on the road under controlled circumstances. This is obviously the biggest market segment. It's not quite here yet, and it's going to come along behind autonomous shuttles, drawing a lot of experience from what's discovered in the operation of autonomous shuttles to realize autonomous driving and autonomous aircraft coming up. But it's going to be a little bit later, and I think all of the audience concurs on that. Well, not all of them, everyone except 16% concur on that one. We're going to turn now to questions from the audience to our panelists. I want to call all three of our panelists back to the microphone, and we have a number of questions for you. One for Roger. Why is the highly scalable aspect important? Why was KVH's PIC built with highly scalable manufacturing technologies?
Okay. So adding more automation and manufacturing process improvements allows us to scale the volumes, achieve the levels of quality and reliability that we need to deliver sensors with improved performance and reliability. And this is key for helping FOGs compete against MEMS pricing for high quantity mass production needs.
Yes, so Skip, you have to remember that semiconductor processes are really developed for producing millions and hundreds of millions of things. So it's not about tens and hundreds and even thousands, it's about millions. It's really built for that, it's designed for that, and that's what today's electronics industry is built on. And so the whole goal of putting photonics into those sorts of processes is to allow that kind of scaling as the markets continue to ramp here in these different areas that we've talked about.
Thanks very much. Roger, does C-swap still matter in autonomy? We're talking about shuttles and autonomous cars, as our audience said, the fastest upcoming applications. Does C-swap still matter for those?
Yes, I think it depends on the application and the specific platform needs. In land, ground, autonomous applications, weight and size are less important than they would be for aerial or subsea. But there are other factors, as I mentioned, like price that matter as well, and performance. Yeah.
All right, coming back to you again, Roger, does KVH have plans to use its PIC in all of its products?
Yes, the technology will be integrated into our products, beginning with our high-performance IMUs and INSs and the DSP 1760 gyros. The PIC technology is giving KVH much more flexibility to provide a broader range of performance based on coil lengths, different sources, that supports a wider range of applications. KVH is known for our custom solutions, and we'd be happy to talk with anyone about your specific needs.
All right, a rather detailed technical question for you, Ralph, next, from somebody in the audience who's obviously highly familiar with inertial technology. Aside from the errors that we've covered so far, bias and scale and random walk and so forth, how much is known about these three factors: stability of cross-axis sensitivity, G and G squared sensitivity, and sensitivity to angular rate and annular acceleration?
Yeah, I mean, those other sort of higher order error terms, depend on the specifics of the sensor geometry. And you usually need to test to determine if they are, first of all, if they're even present at all. And, and then what is their stability if they are there, dependent on your application space. Those are error terms that maybe you may not even need to compensate for. This really depends on the accuracy you're trying to achieve. Those types of terms are sort of usually kind of built in, not designed in. So you really need to sort of test to see if they're present in the first place.
All right. Another question for you, Roger. Are there autonomous applications that the KVH photonic-based products are particularly suited for?
Okay. Yes. KVH sensors can perform with precision and reliability in any environment, but particularly those where GNSS may not be continuously available. It could be inertial sensing, and KVH photonics sensing fogs will be key components in sensor fusion integration, and those applications particularly for harsh or demanding environments such as subsea or aerial.
And continuing with you, Roger, what is the biggest advantage of photonic-based fogs over traditional fogs?
Great question. So from my standpoint, which is not technology-based, it's product-based. And what the biggest advantage of photonic-based fogs is going to offer over our traditional fogs is increased reliability, more dependability, and more customization and performance ranges.
Okay, and another question for Ralph. Which gyro technology do you think will mature first for the same C-swap, MEMS, or RFOG, and how much time do they have before Cold Atom comes in for a further disruption to the market?
I would say MEMS has a leg up there because they already have the C-swap, and they're just trying to move into a higher performance space. Some of the developmental MEMS that is sort of pushing the performance envelope. They are a little bit larger scale than what's typical, but I don't think you ever want to bet against silicon as far as making it into the marketplace. With regard to the cold atom technology is really, really cool. That is, at the moment, not a compact form factor technology. There is a pathway to get to a form factor that's sort of typical of a bulk-sized inertial instrument. But as far as a miniature cold atom, I don't see it, at least not in any time in the near future.
Thanks, Ralph. We had a couple of people asking about that cold atom technology. Not in the near future is the answer. Question for you, Skip. How do you expect the performance to change over the next few years due to photonic integrated chip technology?
Well, as Roger said, the goal here really provides improved reliability, robustness, but the other important factor is the PIC allows us scalability up and down the performance range. So the factors that people noted are important, bias, scale factor, A or W. You want to be able to improve those when necessary, but of course the overall performance is not only set by the PIC, it's set by the accelerometers you use, the electronics, and the overall system parts there. And so the whole goal here really is to allow us to scale up and down the performance stack depending on the individual customer and market needs for a given application.
Thanks very much, Skip. Well, we've run the course of our webinar. I want to encourage everyone in the audience to share the contents of this webinar with your colleagues, and you'll be able to do so via the email that you'll receive in a day or two with the contents of this webinar. And of course, you can tell your colleagues that they can sign up for the webinar independently. The registration will be still available and can be downloaded after the webinar. Before we wind up, I want to call each of our panelists back to the microphone with any concluding remarks that they may have. Ralph, closing remarks.
Yeah, I thought the second poll question was interesting, and then some of the questions from the audience where bias instability polled as the most important parameter people were concerned with, and that's always the toughest thing to achieve. And like some of the higher order terms, one of the questions came in, bias instability is never designed into an instrument. It's always built in. It comes from asymmetries in the sensor element, electronics offsets, and achieving good bias performance requires a consistency of the instrument build process. So technologies like PIC and silicon MEMS, offer a lot of manufacturing reliability, a lot of fabrication consistency from unit to unit. And so those types of technologies support the whole battle against bias instability.
Thanks, Ralph. Skip, some final thoughts from you.
I appreciate the opportunity to share what's been quite a lengthy testing effort and good comments and questions. Really appreciate Ralph's starting kickoff there about the technology and the roadmap.
Thanks, Skip. And Roger, final thoughts.
Well, I think it's an exciting time for KVH fiber optic gyros with the emergence of the new photonic integrated chip. As we look forward to the future, we see different autonomous navigation markets and needs. And the beautiful thing that KVH sees is that this technology allows us to make a flexible product to address those needs that will ensure a more affordable more manufacturing scalable solution.
Thanks, Roger. It is a beautiful thing to see applications opening up to new possibilities with the advances in inertial technology, specifically what we've looked at today, the photonic integrated chip. I'm going to refer our audience back to the resources slide, and again, you'll get these slides very shortly to be able to examine further, review the webinar. The webinar will be recapped in an upcoming issue of either Inside GNSS or Inside Unmanned Systems magazines. And I want to thank all of our panelists, Ralph, Skip, and Roger, for bringing this innovative content to us and to our audience. I want to thank the audience for attending, and we hope that you both enjoyed it and profited by it. I want to thank KVH for sponsoring the webinar and making it possible for us to bring it to you. And with that, we'll close out the webinar. Thanks, everyone. Stay safe out there. And Lori, back to you.
All right. Thank you, Alan. And again, most importantly, thank you for joining us today. It's Lori Dearman saying, hope we see you on the next one. Bye for now.